In this lesson, we're going to look at how dominance can be used to reduce a payoff matrix for a two-player zero-sum game. So we're going to start off just by answering a question from last lesson. You may want to pause the slide now and try to answer it first. So in part A, we are asked to define the meaning of the term zero-sum game. So in this, you would need to describe how in a zero-sum game, the amount that one player wins is equal to the amount that the other player loses each time. So therefore, the two scores will always add to zero, hence zero-sum. In part B, we are then asked to show that the game has no stable solution. So for this, we first of all need to find the minimum value in each row. That is the row min. Remember that this is the worst case scenario for the player on the left hand side, in this case Rowan. So the row minimum, we've got -4, -1, -3. We now need to find the maximum of those. The maximum value of that is -1. So we would write max row min equals -1. We're then going to find the column maximum. That is the worst case scenario for each of the choices for the second player, in this case Colleen. So we've got 1, 5, 4, and here we want to find the minimum value, so we're going to circle that, that's 1. So that is the min call max. We need to state both of these things to start with, and we then need to state that these two values are not equal. So max row min does not equal min call max. This explanation is necessary in order to get the explanation marks. Therefore, there is no stable solution to this game. Remember that a stable solution means that there is no incentive for either player to play a strategy other than playing safe. So for this zero-sum game, we're going to consider whether there are any strategies that player A should never play and why. And then similarly, whether there are any strategies that player B should never play and why. You might want to pause the slide now and consider these questions. So we can see that for player A, choosing strategy 3 will always be better than choosing strategy 1, regardless of how player B chooses. So we can see here, for example, if player B chooses option 1, then A can either win 0 or win 1, so winning 1 would be better. If B were to choose option 2, A will either win 1 or 2, winning 2 is better. Or if B chooses option 3, A will either lose 1 or win 3, and winning 3 is better. So in this case, choosing option 3 will always be better for A compared to choosing option 1. So option 1 should never be played by player A. We can therefore remove that option from the payoff matrix. Similarly, for player B, remembering that the numbers in the table are losses for B, we can see that strategy 1 will always be better than strategy 2, regardless of what A chooses. So we can see here, for example, if A were to choose option 1, then B will either win nothing or lose 1. Obviously, nothing is better. If A were to choose option 2, B will either win 2 or lose 3. Winning 2 is better. And if A chooses option 3, then B will either lose 1 or lose 2. And although they both involve losing 1 is better. So we can see that B will always choose strategy 1 over strategy 2. So therefore, strategy 2 can be removed for B. Therefore, the payoff matrix can be reduced from a 3x3 down to a 2x2. See that we've still called the options the original labels that they had in the original table, just that we've removed the options that are not worthwhile for each player. If you compare two strategies, then one strategy is dominant over another if for every choice that the other player makes, that one strategy will always be better than the other, either better or the same. So you would compare under each of the choices for the other player what the outcome would be for the player you're considering, and if one strategy is always better, then you would say it is dominant over the other one. You would write it as, for example, strategy 3 is dominant over strategy 1. You'd also need to give an explanation in an exam, so you would explain explicitly why one strategy is dominant over another by using inequalities. So you'd say, for example, 3 is greater than 2, 4 is greater than -1, and so on. You can therefore then reduce the size of the payoff matrix using dominant strategies in order to continue with calculations. Pause the slide now, and for each of the 4 payoff matrices, consider whether any strategies dominate any other strategies. So we can see that for the first game, strategy 1 dominates strategy 2 for B. That is because each of the values under each of A's choices, the values for strategy 1 are always smaller than the values for strategy 2, and remember that small values are preferable for player B. So for the second matrix, we can see that strategy 1 dominates strategy 3 for player B. That is because each of the values in strategy 1 is always smaller or equal, in this case, than the corresponding value in strategy 3. Remember that in an explanation in an exam, you would also need to explain why. So you would say because -2 is less than 1 and -1 is equal to 1. So just saying that it dominates isn't quite enough. You also need to give numerical justification as well. For the third game, we can see that strategy 3 for player A dominates strategy 1. That is because 2 is greater than 1, -3 is greater than -4, and -1 is greater than -3. We can also see dominance in the options for B. So strategy 2 always dominates strategy 1 for player B. There's another example of dominance for player B. We can see that strategy 2 dominates strategy 3. And then finally, for the fourth game, we can see that for player A, strategy 1 dominates strategy 3. And for B, strategy 3 dominates strategy 2, reducing the matrix to this one here. Now complete exercise 6.2 on page 94.